I've made a few videos in the past on reaction kinetics, basically rate of a chemical reaction. I've looked at collision theory, surface area, concentration, temperature, and the use of catalysts. Now let's take a bit of a deeper dive and we'll introduce the rate expression, or the rate law. And this video comes with a massive shout out to Gabby. To determine a reaction rate from experimental data, we typically measure how the concentration of either the reactants or the products changes over time. This data can then be used to determine the rate law and the rate constant for the reaction. The most common method is the method of initial rates, where we vary the initial concentrations of reactants whilst keeping other factors constant, and measure that initial reaction rate. If you look at a graph of concentration of reactant and product, it will generally look something like this. We see that the reactant concentration starts high and gradually fades off, and the product concentration started at 0 and builds up. Now, you could actually measure the reaction rate at any stage of the reaction lifetime. If you picked 2 points on the graph, you could calculate the slope between those 2 points, and that would give you the average reaction rate between those 2 points. Or if you wanted instantaneous reaction rate, you would simply draw a line tangent to the curve, and the slope of that tangent line would be the instantaneous reaction rate at that time. But it's much easier just to start right at the beginning. We have no product present, and that's a good thing for any reversible reaction. There's no product to be forming the reactant again. And it's also just a much simpler process. So we look at the initial reactant concentrations. And what we do is we change the concentration of one reactant, but keep the concentration of the other constant, and see how that affects the reaction rate. By doing that, we can determine the order of the reaction with respect to each reactant. From those, we can get the overall reaction order. We can also write the rate law, or the rate expression, and determine the rate coefficient, or the rate constant. Let's go through a couple of examples. So we'll look at concentration versus time data. It doesn't have to be concentration. You could look at the volume of a gas produced, or a mass change, or a color change, etc. But really, concentration versus time is the standard for reaction rates. Now, the rate of reaction is defined as the change in concentration of a reactant or a product over time. As I mentioned, if you're after the instantaneous rate, you would plot a graph of concentration versus time and draw a tangent to the curve at the point of interest. You'd then find the slope of that tangent, and that is your instantaneous rate. In terms of units, you always need to make sure you have the correct units. We're talking concentration in mole per litre and time in seconds. So this gives rate units of mole per litre per second, or mole per litre second. Now, if we have data from multiple experiments with varying concentrations, we can determine the rate law. The rate law is given as the rate is equal to K times the concentration of A to the power of M multiplied by the concentration of B to the power of N. Now, A and B are just the different reactants. Remember, square brackets say concentration of. So A in square brackets says the concentration of A, and that's of course in mole per litre, or molar. M and N, I've seen those written as X and Y, or alpha and beta, but I'm just going to go with M and N because that's what I'm used to. For our first example, we have A reacting with B and forming some products. We don't really care what the products are. It's A and B that we're interested in, well, their concentrations. So we have this table. Now this is looking at 3 experiments. We can see in the first experiment, the concentration of A was 0.1 molar. The concentration of B was also 0.1 molar. And the initial rate of that reaction was 2 by 10 to the minus 3 mole per litre second. Now, if we look at experiment 2, we can see the concentration of B was kept constant, but the concentration of A was doubled. Now, this has affected the initial reaction rate. Now we're looking at 4 by 10 to the minus 3 mole per litre second. But then a third experiment was done where the concentration of A was put back to the original 0.1 mole per litre, but the concentration of B was doubled to 0.2 mole per litre. This had the effect of multiplying the initial rate by 4. We've gone up to 8 by 10 to the minus 3 mole per litre second. So using this data, let's see what we can do. Our first point would be to write the rate law. So rate equals K. So remember, K is just the rate coefficient or the rate constant, multiplied by the concentration of A to the power of M, multiplied by the concentration of B to the power of N. M and N are those orders that we're going to need to find. First, we'll find the order with respect to A. So we need to find two experiments where the concentration of B was constant. Well, that's experiment 1 and 2. So we will compare those two experiments, 1 and 2. Now, we've already said the concentration of A doubles. It went from 0.1 to 0.2 molar. And the rate also doubled. It went from 2 by 10 to the minus 3 up to 4 by 10 to the minus 3. So in comparing these two experiments, we write rate 2 over rate 1 is equal to the concentration of A in experiment 2 over the concentration of A in experiment 1. Now that's all raised to the power of M. And then we plug in our numbers. And our numbers say, well, rate 2 over rate 1 is 4 by 10 to the minus 3 over 2 by 10 to the minus 3. And the concentrations of the second experiment over the first experiment, just looking at the concentration of A, that's 0.2 over 0.1. But remember, this is in brackets to the power of M, and it's that M that we need to work out. That's the order that we're trying to find with respect to reactant A. So the numbers from the rate comparison gives 2, and the numbers from the concentration comparison gives 2 to the power of M. So we have 2 equals 2 to the power of M. Well, what could M be? Anything raised to the power of 1 is itself, isn't it? So 2 to the power of 1 equals 2. M must be equal to 1. So the reaction with respect to A is first order. Now we need to do the same thing with respect to B. So we're going to choose the two experiments where the concentration of A stays the same. This is experiment 1 and 3. So if we compare these, we see that the concentration of B doubles from 0.1 to 0.2, and the rate increases by a factor of 4, from 2 by 10 to the minus 3 to 8 by 10 to the minus 3. So again, we'll write it down. Rate 3 over rate 1 we'll put. That is equal to the concentration of B of the third reaction over the concentration of B of the first reaction, and this is all raised to the power of N. Great, now we plug in our numbers. We have 8 by 10 to the minus 3 divided by 2 by 10 to the minus 3 is equal to 0.2 over 0.1. That's all raised to the power of N. Well, the 8 over the 2, that's going to give us a 4. The by 10 to the minus 3s are going to cancel out. So the rate comparison gives us 4. The concentration comparison gives us 2, because it's 0.2 over 0.1. So that's 2. But remember, that was raised to the power of N. So we have 4 equals 2 to the power of N. What does N equal? Well, N equals 2, because 2 squared equals 4. So we've found now that the order with respect to reactant B is 2. If we were asked for the total order overall, well, we just add the orders of the reactants. So for reactant A, that was first order. For reactant B, that was second order. So this would be third order overall. Anyway, let's go back to that rate law. We had written the rate equals K multiplied by the concentration of A to the power of M, but now we know that's a 1, multiplied by the concentration of B to the power of N, but now we know that's a 2. So we'll put that 1 and the 2 in to give us our final rate law, and then we can find the rate constant, or the rate coefficient, K. And we can do this by using any of those 3 original experiments. Just pick one at random. Let's look at experiment 1. We've got numbers to put in. We've got a concentration for A. We've got a concentration for B. We've got a rate. And now we've got the orders that those concentrations are raised to. So we can just rearrange the equation, and we can find that K is equal to 2 by 10 to the minus 3 divided by 0.001 equals 2 liters squared per mole squared per second. Let's look at another example now. Here we see peroxide disulfate reacting with the iodide ion to produce a couple of sulfate ions and a triiodide. Now, peroxide disulfate can be a bit tedious to say or to write, So we'll just state that the concentration of that ion, let's just call it concentration of S, and the concentration of the iodide, we'll just call it concentration of I, because it's much easier to talk about S and I. Just like in the previous example, we were talking about A and B. In this case, we'll just call them S and I, just for convenience. So we have here a table of data from 3 experiments. Experiment 1 and 2, the concentration of S, the peroxide disulfate, that is constant at 0.08 mole per liter. But the concentration of the iodide ion, so the concentration of I, we can see has halved from 0.034 to 0.017 mole per liter. If we compare experiments 2 and 3, we see now the concentration of I is the same and the concentration of S has doubled from 0.08 to 0.16 mole per liter. And we can also see how the rate of each experiment has changed accordingly. So let's go through the same steps that we did before. So first up, we write the general rate law. So we have the rate is equal to K times the concentration of S to the power of M times the concentration of I to the power of N. Then we'll work out the order with respect to each reactant. Let's start with reactant S. The concentration of S doubles from 0.08 to 0.16 molar, and the rate also doubles from 1.1 by 10 to the minus 4 to 2.2 by 10 to the minus 4. So we write our comparison now. Rate 3 over rate 2 equals the concentration of S3 over the concentration of S2. That's all raised to the power of M. We plug in our numbers. 2.2 by 10 to the minus 4 over 1.1 by 10 to the minus 4 is equal to 0.16 divided by 0.08, and remember that's all raised to the power of M. The rate comparison brings us down to 2. The concentration comparison also brings us down to 2, so we're left with 2 equals 2 to the power of M. And this is very similar like the previous example. M has to be 1, because 2 to the power of 1 equals 2. So the reaction is first order with respect to reactant S. And we do the same thing with the other reactant. So let's work out the order with respect to reactant I. Concentration of I halves from 0.034 to 0.017 molar. And we can see the rate also halves. It was 2.2 by 10 to the minus 4, and it goes down to 1.1 by 10 to the minus 4. So let's do our comparisons. Rate 1 over rate 2, concentration 1 over concentration 2 raised to the power of N. Put in the numbers, 2.2 by 10 to the minus 4 divided by 1.1 by 10 to the minus 4 is equal to 0.034 divided by 0.017, and that's all raised to the power of N. Well, the rate comparison comes down to a 2. The concentration comparison also comes down to a 2, and that's raised to the N. So we have 2 equals 2 to the power of N. N must be equal to 1, much like the previous example for reactant S. So in this case, the order with respect to the iodide ion is 1. The order with respect to the peroxide sulfate ion is also 1. So they're both first order with respect to each reactant. Overall, the reaction would be order 2, because we simply add the orders of the reactants to get the overall reaction order. So overall, the reaction order would be 2, but for each reactant, it's 1. And then we rewrite the rate law with our powers now. Now that we know what order it is, what those powers are, they're both 1. So we have the rate is equal to K times the concentration of the S2O82 minus to the power of 1, multiplied by the concentration of iodide to the power of 1. And then we can determine K, the rate constant. Plugging in the numbers to that rate law, we see that K is approximately equal to 0.0809 litre per mole per second. Now, one question that sometimes crops up is, well, when you're comparing this experiment with that experiment and you have rate over rate and concentration over concentration, which one do you put on top? Which is the numerator? The first experiment information or the second experiment information? Well, the answer is it really doesn't matter. You could put experiment 1 over experiment 2. So it would be rate 1 over rate 2 is equal to concentration 1 over concentration 2 to the power of M. Or you could flip it and have rate 2 over rate 1 is equal to concentration 2 over concentration 1 to the power of M. The important thing is you keep it all the same. So if your rate 1 is on top of rate 2, you would make sure your concentration 1 is on top of concentration 2, and then raise that to the power of m. So long as you keep that the same, then you'll be grand. It works out either way. Having said that, it is generally easier and less error-prone to put the larger values on top. It's not a rule, it's just for convenience. So that's a bit of a deeper dive into reaction rate using the rate law. Any chemists watching this video? Have fun! Well, that's the video done. If you liked it, brilliant. Hit the like button and leave me a comment too. Now you know what to do. Go hit that subscribe button. We'll see you next time.